Now we are going to see the electrical properties of the colloidal particles. See, the particles and the medium both are charged, but the total charge carried by the particle and the medium are equal but opposite in sign. Suppose if the medium is negatively charged, then the particles are positively charged. If the medium is positively charged, then the particles are negatively charged, but the total charge of the medium and the particles are always equal in magnitude. It is because the system will always try to maintain its electrical neutrality. So what will happen? If the particles are positively charged or negatively charged, each particle will carry the same charge. So that will prevent the particles coming closer and getting accumulated or getting coagulated. So this is one of the reasons why the colloidal system is stabilized by the electrical charges. See, there are electropositive colloids and electronegative colloids. This positive or negative nature is the nature of the colloidal particles. Is the nature of the colloidal particles. See, the metallic hydroxides and metal dispersions like bismuth, lead, and iron, or the indicator methyl violet or methylene blue. These are all some of the examples of our electropositive colloids. Whereas metallic sulfides, the pigments like Prussian blue, metals like gold dispersion, silver dispersion, platinum, silicic acid, tannic acid, or mastic. These are all electronegative colloids. These are electronegative colloids. When you think of the electrical double layer, the electrical setup in the colloidal system is in the form of electrical double layer. And in the electrical double layer, you can see this is something like the solid and the liquid interface. Look here. Suppose if a solid substance is here and the positively charged particles are having the tendency to adhere on the surface, then the first layer is called fixed layer. And the second further layers are called diffuse or mobile layers. Now what will happen? The first fixed layer is all of one particular charge, and the diffuse layer will have both negative and positive charges, but the total charges will be always equal. Similarly here also, if negative charges are the fixed layer, then the positive and the negative charges will be in the diffused layer, but the total charges will always be the same. This will produce, what will happen? There will be a small potential difference produced between the fixed layer and the diffuse layer, and this potential is called Zeta potential. And also, this is actually the double layer is existing between solid and liquid interface, which was first proposed by Helmholtz, and then it was further constructed by Guy and Stern. And they are the scientists who further worked on the same thing and came out with different ideas on the electrical double layer structure. Now, see, the ions preferentially absorbed on the surface and their counter ions are in the diffused portion. So the existence of charges of opposite signs on the fixed and the diffuse parts of the double layer leads to the appearance of a difference of a potential between the two layers, and this potential is called zeta potential or electrokinetic potential. So this electrokinetic potential or zeta potential is called Z, which is equal to 4 pi eta u by d, where eta is the coefficient of viscosity, u is the electrophoretic mobility, and D is dielectric constant, where U is called the electrophoretic mobility. Means you have to understand what is electrophoresis. So look at this diagram. This is electrophoretic setup. I have filled this with the colloidal substance, the U tube with the colloidal substance, and two electrodes are immersed, and the electrodes are connected to the electrical circuitry. If the colloidal particles are negatively charged, then the colloidal particles will move towards the positively charged electrode, and you can see from this line onwards, the colloid begins, and this is only the solvent, the dispersion medium, because the colloidal particles, see, originally the solvent or the dispersion medium are of the same level, because all the fluids will maintain the same level. But because of the electrical influence, the colloidal particles have moved more towards the positive electrode. It has almost come here, because the colloidal particles are negatively charged. So the distance, originally it was here, see, and now it is here. So what is the distance traveled by the colloidal particles on the application of electricity? So the distance traveled by the particles in 1 second under a potential gradient of 1 volt per centimeter is called the electrophoretic mobility of the colloidal particles. Normally, the value is 10 to 60 into 10 power 5 minus 5 centimeter per second per volt per centimeter. So this is called electrophoretic setup. So this movement of the colloidal particles can be seen by a cathetometer, and also the colloidal particles will move towards the oppositely charged electrical plate, and from this you can find out what is the charge of the colloidal particles, and also you can find out the electrophoretic mobility of the colloidal particles. This is the application of electrophoresis. This is called electroosmosis. What is electroosmosis? I am just confining the colloidal substance between two membranes, and these two membranes are called semi-permeable membranes, which will prevent the motion of the colloidal particles, but which will allow the motion of the dispersion medium. So when I apply electricity, what will happen? As the colloidal particles are restricted from motion, then the dispersion medium would move in a direction opposite to that which the colloidal particles would have normally taken. So if the colloidal particles move towards a negatively charged electrode, then the dispersion medium will move towards positively charged electrode. Then you can see the dispersion medium has a risen level on the positively charged electrode, and the level is down on the negative side. So this is called electroosmosis. So when the dispersed phase is prevented from movement, the dispersion medium moves in the opposite direction. So in electroosmosis, when the colloidal particles are restricted, the dispersion medium would move in a direction opposite to that which the colloidal particles would have normally taken.